Deep within the boundaries of the Hercules constellation, sitting roughly 1,200 light-years away from our own world, drifts an alien planet that stretches more than double the entire diameter of Jupiter. Human intuition tells us that a world of this staggering magnitude must be a crushing gravity monster, an absolute titan of overwhelming planetary force. Yet it is completely the opposite. HAT-P-67b carries less than half of Jupiter's total mass, possessing an overall density lighter than a common marshmallow. Modern space observations have verified that its outer atmosphere is bleeding out into the void of space at an unbelievable rate of 10 million tons every single second. This evaporating gas trails ahead of the world in a massive ghostly stream of helium gas that extends outwards more than 130 times the planet's own radius. Within a few 100 million years, this fragile giant will be completely consumed by its own dying star. This is not the massive planet you thought you would find. This is a world so impossibly swollen and puffed up that the traditional definition of a planet scarcely applies to it. If you are ready for cosmic journeys that completely break your expectations of what the universe is capable of creating, consider hitting that like button and subscribing to the channel. It truly helps us out immensely and keeps these deep space stories coming your way. Now, settle in, get completely comfortable, and let us begin our journey. Close your eyes for a moment and picture the single largest planet existing in the cosmos. No matter what your mind builds, that picture is likely incorrect. However, the exact error you make uncovers a fascinating truth about how human beings perceive physical size, power, and what an actual planet is expected to be. So let us begin with the exact image you probably conjured up. You likely pictured something immensely heavy, a colossus with a gravitational pull so fierce that it could instantly flatten spaceships and pull down moons. You imagined a significantly scaled up version of the grandest planet you're already familiar with. You pictured a much bigger version of Jupiter, and that basic instinct is completely reasonable. Jupiter is the undisputed ruler of our solar system, and every single characteristic it possesses radiates absolute dominance. It measures roughly 11 times wider than Earth, meaning you could pack more than 1,300 Earths neatly inside its massive volume and still have plenty of room left over. Its total mass is 318 times greater than our own home planet. In fact, it weighs significantly more than every single other planet, moon, asteroid and comet in our solar system combined, and then doubles that immense number just for good measure. Jupiter is not merely the largest body orbiting our central sun, it acts as the gravitational anchor that physically sculpted the orbits and architecture of every single world around it. If you could somehow survive standing on the swirling cloud tops of Jupiter, your weight would instantly become 2.5 times greater than it is on Earth. The crushing atmospheric pressure far beneath those clouds rises to extreme levels that would flatten a modern nuclear submarine in a matter of moments. Winds howl across the planet at 350 miles per hour. The iconic Great Red Spot, a massive storm system that has been spinning for centuries, is so incredibly large that our entire Earth could sit safely inside it with room to spare. Lightning strikes crackling through Jupiter's deep atmosphere unleash energy outputs 1,000 times more powerful than any lightning found on Earth. Furthermore, the invisible radiation belts looping around the planet are so fiercely intense that they would deliver a deadly dose to an unprotected human being within minutes. This is a world defined by absolute overwhelming force. The reach of Jupiter's gravity is so vast that it has successfully trapped 95 known moons, several of which are massive enough to be considered full-fledged worlds on their own. Ganymede, its grandest satellite, is actually larger than the planet Mercury. Europa, concealed beneath a thick outer shell of solid ice, holds a vast global ocean that likely contains far more liquid water than all of Earth's oceans put together. Io, constantly tugged and squeezed by intense gravitational tidal forces, explodes with a volcanic rage unmatched by anything else in our planetary system. Jupiter functions as a vital cosmic guardian as well. Its immense mass successfully pulls comets and asteroids off course, preventing them from slamming into the fragile inner solar system. Without the presence of Jupiter, Earth would be struck by devastating space rocks far more frequently than it is. Because of this, a number of scientists suggest that the presence of a massive gas giant in the outer solar system is precisely what gave complex life enough stable, peaceful time to evolve on our planet. Jupiter doesn't just rule our planetary neighbourhood, it very well may have made our existence possible in the first place. Now, this is precisely where human expectation steps in with a highly specific logical rule. If Jupiter exhibits this level of power at 11 times the width of Earth and 318 times its weight, then the single largest planet in the entire universe must be all of these statistics heavily multiplied. It should be vastly wider, heavier, denser and far fiercer. It should look like Jupiter on steroids. Its weather system should be far more violent, its gravity should be infinitely more crushing, and its radiation should be profoundly more lethal. Its collection of moons should be vastly larger. Everything regarding the largest possible planet should reflect the absolute maximum limit of what planetary physics can create. This line of thought is not just random guesswork, it directly mirrors a clear pattern that humans witness everywhere in the natural world. The largest elephants are naturally heavier than smaller ones. The tallest man-made skyscrapers require far more steel than shorter structures. The most massive stars in space contain vastly more physical material than average-sized stars. When objects increase in physical size, they almost always become heavier and significantly more powerful. Physical mass scales directly alongside physical volume. Power scales directly alongside mass. This specific relationship holds true across almost every single area of normal human reality. For centuries, this exact same rule appeared totally solid within planetary science too. Early astronomers were familiar with 9 worlds, which later became 8 after Pluto was officially reclassified. The rule was incredibly clean and simple. The solid, rocky planets close to the Sun were physically small and highly dense. Earth, the largest member of this group, measured about 8,000 miles across, with a physical density sitting at roughly 5.5 grams per cubic centimetre. Meanwhile, the gas and ice giants residing in the outer solar system were physically massive and comparatively less dense, yet they still remained deeply heavy and impressive. Jupiter sat proudly at the absolute peak of this cosmic system. It was the biggest, the heaviest, and the most gravitationally intense. This direct link between physical size and total mass seemed entirely bulletproof, looking very much like an unyielding law of nature. But everything changed when astronomers began discovering planets circling completely different stars, and this comforting pattern was thoroughly shattered. The very first confirmed exoplanet found orbiting a Sun-like star was located back in the year 1995. This planet, named 51 Pegasi b, was detected by Michel Mayor and Didier Queloz, utilising precise radial velocity tracking at the Haute-Provence Observatory. The discovery sent shockwaves straight through the scientific community for a specific reason that feels remarkably minor by today's standards. 51 Pegasi b was a massive gas giant holding roughly half the physical weight of Jupiter, but it zipped around its parent star in a mere 4.2 days. This tight path placed it significantly closer to its home star than Mercury is to our own Sun, absolutely no one expected to discover a planet the size of Jupiter sitting in such a blisteringly hot, tight orbit. The reigning scientific models of planet creation clearly stated that massive gas giants could only form far away from their parent stars, out in the freezing outer zones of planetary systems where volatile ice could slowly pile together to build heavy planetary cores. Finding a gas world nearly scraping the surface of its star was the cosmic equivalent of finding a pristine snowman standing directly inside a roaring blast furnace. This single discovery completely opened the scientific floodgates. Within just a few years, astronomers located dozens of highly similar planets. These were giant worlds locked in tight orbits with scorching surface environments. They quickly picked up a popular nickname that remains to this day: hot Jupiters. These newfound worlds instantly demonstrated that the link between physical size and total mass was far more intricate than anyone had previously believed. Some of these hot Jupiters were significantly heavier than Jupiter itself, while keeping roughly the exact same width. Others turned out to be much lighter than Jupiter, while being noticeably wider. A chosen few were dramatically wider than Jupiter, while retaining only a tiny fraction of its physical weight. The beautiful correlation that worked flawlessly inside our own local solar system was not an ironclad cosmic rule. It was merely a local planetary coincidence. As technical detection strategies grew more advanced, the official list of known exoplanets absolutely exploded. Transit photometry, a method where scientists monitor the subtle dimming of a star's light as an orbiting planet glides directly in front of it, allowed for incredibly precise calculations of planetary sizes. At the same time, radial velocity tracking, which monitors the slight physical wobble a planet creates in its host star, offered helpful mass calculations. Merging these two independent systems gifted astronomers with a revolutionary new data set: the ability to calculate the exact physical density of distant worlds. And the resulting density data was incredibly strange. Certain gas worlds possess densities highly comparable to Jupiter, averaging around 1.3 grams per cubic centimetre. However, others exhibited densities that were far lower, dropping well below 1 gram per cubic centimetre, which is less than the density of plain water. A handful of planets registered densities so shockingly low that they seemed to defy basic physical logic. These were planets possessing the total volume of Jupiter, but weighing less than Saturn. These were worlds with the massive width of a giant planet, but with the actual inner substance of something resembling hot, glowing fog. These unique worlds were the inflated hot Jupiters. They were planets puffed up to enormous sizes that their basic mass alone could never explain. Standard scientific models regarding planetary interiors state that a gas giant of a specific mass and age ought to steadily shrink down to a precise radius as it naturally cools over long stretches of time. These traditional models function beautifully for cold gas worlds located far away from their stars. Yet, for worlds trapped in tight orbits and drenched in blinding stellar radiation, the calculations regularly underestimated the actual sizes observed in space. These worlds were far too large, not by a tiny amount, but by 20, 30, and sometimes even 50% or more. This ongoing inflation problem quickly grew into one of the most prominent mysteries in all of exoplanet science. What was forcing these giant worlds to puff up so far past their calculated limits? Where was this massive injection of extra energy originating from? Why did certain hot Jupiters puff up to a spectacular degree, while other planets resting in highly similar orbits remained completely compact? The complex questions seemed to show up far quicker than the actual answers. Several possible explanations were put forward by scientists. One idea was ohmic dissipation, a process where powerful electrical currents created by raging atmospheric winds travelling through a planet's magnetic fields dump intense heat straight down into the core. Another concept was tidal heating, where the relentless gravitational tug-of-war between a planet and its star physically flexes the world's interior, generating extreme internal friction. There was also advective heat transport, where savage global weather systems absorb energy from the blisteringly hot day side and shove it deep down into the planet's core, stopping it from cooling down normally. Finally, scientists considered enhanced atmospheric opacity, where unique chemical patterns in the air successfully trap incoming heat far more effectively than standard models predict. Each of these individual concepts managed to explain specific cosmic observations, but none of them could successfully account for the entire spectrum of wildly inflated planet sizes found throughout space. Yet, even while the exact technical details continued to be heavily debated, one truth became crystal clear. Sitting too close to a star fundamentally transforms what a gas world can become. A gas giant resting in the deep, cold outer zones of a planetary neighbourhood behaves exactly the way science textbooks describe. It forms, it gradually cools down, and it shrinks to a highly predictable size dictated by its mass and ingredients. It sits out there completely stable for billions of years. However, if you take that exact same planet and push it right up close to its star, just a few stellar diameters away, everything changes instantly. The relentless stellar radiation pumps massive amounts of raw energy directly into the planet's atmosphere. That intense energy travels deep into the core through complex pathways that scientists are still actively trying to decipher. The world expands massively. Its overall density plummets. Its basic inner structure alters into something that Jupiter wouldn't even recognise. This is the exact hidden reality that most average people completely overlook when they hear the term largest planet. The word largest, when applied to worlds in space, brings along an automatic mental assumption. We naturally assume it refers to the most massive world, the most gravitationally commanding, and the most physically terrifying object in every single category. We think that the widest planet must also be the heaviest planet. We think it must be an absolute super Jupiter, a world that makes our own local gas giant look tiny by comparison. But a planet's physical radius and its total mass are two completely different things. They do not tell the same cosmic story. A world can boast an absolutely massive radius while holding on to a surprisingly small amount of actual mass. This specific scenario unfolds when an external force stops the planet from naturally shrinking, when massive amounts of energy are pushed into a planet's interior faster than the world can radiate that heat back out into space. The final result is a world that is enormous in terms of physical volume, but incredibly thin in terms of real substance, acting more like a cosmic balloon rather than a solid cosmic cannonball. Consequently, the grand hunt for the largest exoplanet transforms into a far more complex question than it initially seems. Are we actively searching for the most massive planet, meaning the one containing the maximum amount of physical matter? That specific quest leads you down a path toward worlds that weigh many times more than Jupiter, worlds that are dense, heavy, and gravitationally terrifying. Or are we instead searching for the single widest planet, the one boasting the absolute largest physical radius? That path points you in a totally different direction, leading straight toward heavily inflated worlds, where the absolute imbalance between immense size and actual substance reaches extremes that challenge our baseline understanding of what a planet can be. This specific distinction is vital because it changes what the final answer actually reveals to us. The heaviest worlds are certainly impressive, but they are not particularly surprising to science. They are simply more of what we already know. They offer more gas, more gravity, and more internal pressure. The basic physics scales upward exactly as expected. But the widest planets, the most heavily inflated ones, are truly bizarre objects. Their immense size doesn't come from piling on more physical material. Instead, it comes from their existing material being forcefully stretched, heated, and puffed up into wild shapes that no cold planet could ever replicate. They are the direct results of planetary violence, extreme proximity, and harsh stellar environments turning what should be a standard ball of hydrogen and helium gas into something entirely alien. As of right now, astronomers have successfully verified the existence of more than 5,700 exoplanets. The official catalogue contains an absolutely stunning range of environments. There are small, rocky worlds tinier than Earth, and massive super-Earths that have no comparison inside our own solar system. There are mini-Neptunes wrapped in thick, heavy layers of gas, as well as ice giants and traditional gas giants. There are even worlds that orbit two stars at the exact same time. We have found planets that orbit so agonizingly close to their home stars that their upper atmospheres literally melt, creating weather systems that rain down liquid iron. On the opposite end, we have found lonely rogue planets that drift through the vastness of interstellar space, far away from any star, floating in permanent frozen darkness. The sheer variety is breathtaking. Within this massive database, scientists have identified a small group of planets that sit at the absolute limit of the physical size scale. These are the largest known worlds in existence, not the heaviest, but the absolute widest, and they all group together in a highly specific category. They are almost universally hot or intensely irradiated gas giants locked in ultra-tight orbits. They are nearly all inflated far past what their actual mass would normally suggest. And amazingly, several of them are not even as heavy as Jupiter. That final point is worth emphasizing because it completely shatters human intuition. A number of the largest radius worlds known to modern science are actually lighter than Jupiter, and some are significantly lighter. They are gigantic not because they hold massive amounts of matter, but because the gas they do have has been violently stretched out into a physical volume that normal physics should never permit for that amount of material. They are the cosmic equivalent of cotton candy, massive, incredibly diffuse, and structurally precarious. Among this select group of celestial oddities, one unique planet stands completely alone. There is one specific world that claims the absolute #1 spot on the radius chart within the NASA Exoplanet Archive, sitting in a zone of the mass-radius graph so extreme that almost no other object can survive there. This planet is not the heaviest, nor the densest, nor the most gravitationally aggressive world in the catalogue, but it is one of the most physically swollen, absurdly oversized and structurally fragile objects that has ever been granted the official title of a planet. Its name is HATP 67b. It circles a dying star within the Hercules constellation, resting roughly 1,200 light-years away from Earth. It was originally spotted by the Hungarian Automated Telescope Network using small, wide-field telescopes stationed at two separate locations, the Fred Lawrence Whipple Observatory in Arizona and the Mauna Kea Observatory in Hawaii. Initial data was gathered between 2005 and 2008, with follow-up transit data captured from 2011 through 2013. Its formal confirmation and analysis paper was published in 2017, and the moment astronomers crunched the final numbers, they found a data set that barely made sense. HAT-P-67b boasts a radius of roughly 2.14 Jupiter radii. Let that exact number settle in your mind for a second. This world is more than twice as wide as Jupiter. If you could place it right next to Jupiter, it would dwarf the king of our solar system, the exact same way Jupiter completely dwarfs Earth. Its total volume is roughly 10 times greater than Jupiter's volume. If the biggest planet in our own neighbourhood is represented by a standard basketball, HAT-P-67b would be a massive beach ball sitting right beside it. By any logical metric of physical scale, this is one of the single largest planets ever confirmed to exist. The official NASA Exoplanet Archive explicitly tracks it at the very top of the widest known exoplanets. In terms of pure physical diameter, it is a monster that makes Jupiter look entirely ordinary. But this is the exact moment where the narrative takes a sharp turn, and every single thing you assumed about what the largest planet should be completely falls apart. HAT-P-67b is more than double the width of Jupiter, but it does not possess double the mass. It doesn't even possess the same mass. The most up-to-date scientific calculations, published in 2025 by a research team using the NEID spectrograph on the Wien 3.5 metre telescope, revealed a mass of only about 0.45 Jupiter masses. That is less than half the total weight of Jupiter, coming in at roughly 1.5 times the mass of Saturn, while stretching out to more than double Saturn's physical width. Look at those two contradictory statistics side by side, and let the reality sink in. A planet more than twice as wide as Jupiter, but weighing less than half as much. This wild combination yields a physical density so shockingly low that it initially sounds like a mathematical error, registering at roughly 0.061 grams per cubic centimetre. Now consider the paradox that this world presents. The widest known planet based on its physical radius is completely different from a larger version of Jupiter. It does not carry more mass, it does not have a higher density, and it does not possess more overwhelming gravitational authority. Instead, it represents the exact opposite of everything human intuition leads us to anticipate. To grasp why this environment is so incredibly hostile for the world itself, we can look at the intense conditions present at its orbital path of only 10 million kilometres. Its parent star is already roughly 2.5 times as wide as our Sun, while shining 12 times brighter, meaning it fills a massive area of the planet's sky. If you were able to somehow look out from the upper cloud layers of this planet without being instantly turned to vapour, the star would not resemble the small, modest circle we see from Earth. It would absolutely dominate the heavens, expanding across nearly 20 degrees of the sky, which is roughly 40 times the apparent size of our Sun as seen from our home world. The day-facing side of the planet is continuously blasted with such brutal radiation that atmospheric molecules are torn apart into basic atoms. Elements like sodium and potassium float around as a free atomic vapour, and hydrogen is completely split apart. Under these extreme pressures and temperatures, even materials like iron and magnesium can exist completely as a gas. Meanwhile, the night-facing side experiences an entirely different reality since the planet is gravitationally locked, meaning the exact same face is perpetually pointed directly at the star. The far side of the world never gets any direct starlight. Because of this, temperatures on the dark side drop by hundreds or even more than 1,000 Kelvin, establishing one of the most intense temperature splits found anywhere in the known exoplanet catalogue. Incredible atmospheric winds, which General Circulation Models project can climb to speeds of multiple kilometres per second, constantly try to move this heat from the day side over to the night side. These massive jet streams circle around the equator of the planet, sweeping scorching gas from the bright hemisphere over to the dark side. But this heat redistribution is far from perfect. The night side remains significantly colder, and at the terminator line, the incredibly sharp boundaries separating eternal daytime from endless night, temperatures plunge by hundreds of degrees over distances shorter than the width of an ordinary continent. Clouds can rapidly form and dissolve in thin, narrow bands right along this twilight line. This massive temperature difference drives the intense atmospheric movements that are completely central to the extreme swelling behaviour of the world. The pure force of the radiation slamming into the day side has another major effect. It sets the equilibrium temperature of the world at roughly 1900 Kelvin, which places the planet right on a critical dividing line for exoplanet categorization. Below about 2000 Kelvin, most planetary atmospheres are dominated by molecular chemistry like water vapour, carbon monoxide and methane. Above that specific limit, thermal breakdown shreds these molecules apart, causing the atmosphere to transition into a state dominated by free atoms and ions. Because this planet sits right on this dividing boundary, its day side likely pushes into the atomic state, while its night side manages to keep molecular compounds intact. The world is not just incredibly hot, it exists right at a chemical tipping point where the atmosphere completely shifts from one type of object into another, depending on which hemisphere you are looking at. To fully understand how bizarre this planet truly is, it is helpful to visualize exactly where it sits on a mass radius diagram, which is the foundational chart astronomers rely on to categorize and make sense of planetary diversity. This world sits right at the absolute top of the radius scale among the thousands of confirmed exoplanets discovered so far. Recent scientific studies describe it explicitly as the largest known hot giant planet in existence. When looking strictly at physical width, this is easily among the most massive worlds humanity has ever verified, yet declaring it the largest planet in the entire universe requires a few specific details that honest science forces us to explain clearly. In reality, it is a vast collection of hydrogen and helium gas that contains less total mass than Jupiter, but is spread out over a volume that is roughly 10 times larger. Its overall density is so incredibly low that the gas at its outer surface, to the extent that you can even define a surface, is actually thinner than the gas found inside high-tech vacuum chambers on Earth. It has no crisp edge, and its atmosphere does not simply stop at a clean boundary. Instead, it fades away continuously outward, blending directly into the massive stream of escaping gas that reaches forward along its orbit for a distance equal to 130 times the planet's own radius. At specific wavelengths of light, the world looks 6 times wider than Jupiter, because this escaping cloud of gas blocks starlight far beyond where the actual gravitationally bound atmosphere comes to an end. This raises the question of where the actual planet is in the middle of all of this. Where does the physical object stop and the escaping process begin? These are real physical puzzles that the planet forces scientists to deal with. For a rocky planet like Earth, the answer is perfectly obvious, because the solid surface forms a definitive boundary. For Jupiter, the answer is slightly less obvious, but still manageable, since the visible cloud tops give us a useful proxy for the edge of the world, even though the atmosphere continues above them. For this inflated world, the answer completely breaks down. The planet is simply a slightly thicker pocket within a much larger, diffuse outflow of gas. It is a slightly denser zone inside a thin stream, sitting within the near vacuum of open space. It is not a solid object so much as it is a continuous gradient. While this might sound like a philosophical debate, it has very real scientific consequences. When astronomers calculate the radius of a transiting exoplanet, they are measuring the exact point where the planet's atmosphere becomes thick enough to block out a noticeable amount of starlight. For a tightly packed world, this radius lines up perfectly with the actual physical edge of the object. For this world, The measurement merely captures the outer limit of a highly stretched atmosphere that might not even be fully bound to the planet anymore. The number we point to as the radius is not the actual edge of a solid world, but rather the edge of a specific visibility threshold. The planet expands far past it in one physical sense, while being much smaller than it in another, if by planet you only mean the material that is tightly bound by gravity. This same confusion applies directly to the mass measurement as well. When we state that the world weighs under half of a Jupiter mass, we are describing the total gravitational pull of the object calculated from how it makes its parent star wobble. However, that total mass calculation includes gas that is actively escaping into space at this very moment. The planet's mass is not a permanent, fixed number. It is dropping in real time at a speed of roughly 10 million metric tons every single second. The mass we observe today is not the same mass that existed a million years ago, and it will not match the mass left a million years from now. The planet is a moving snapshot of a destructive process, not a stable object, which is deeply strange to think about. Humans are used to thinking of planets as permanent features of their solar systems. Earth has been around for over 4 billion years, and Jupiter has lasted just as long. The worlds in our own solar system feel completely eternal on a human timescale, and they are incredibly stable even on astronomical timescales. They will easily outlive the main lifespan of our Sun, persisting in some form long after the Sun shrinks down into a white dwarf. This inflated world will not last. Its time as a recognisable planet is entirely temporary. It is not temporary compared to a human life, but it is temporary on the timeline of stellar evolution. Within a few 100 million years, the planet will either completely lose its atmosphere to space, or be entirely swallowed up by its parent star as the star puffs up into a red giant. Either way, the world we see today will completely cease to exist within a cosmic blink of an eye. Now look closely at the mass radius diagram, which is the baseline map that space scientists use to sort and comprehend the massive variety of planets we have spotted. This layout tracks the weight of a world on one side and its structural width on the other. Every single validated alien world that has its mass and physical width verified gets pinned to a specific spot on this layout. This breakdown tells a very clear tale, showing that the vast majority of gas giants pack together into a highly predictable zone on the chart. Worlds that sit close to a single Jupiter mass typically show a physical width that lands between 1 and 1.2 Jupiter radii. As you add more weight past the baseline of Jupiter, the physical width actually stops expanding altogether, and in quite a few instances it even starts to shrink back down. This happens because the increased gravitational pull squeezes the gas together much more tightly and efficiently. This behaviour is a very well apprehended result of how degenerate matter acts under pressure. If you continue to drop more hydrogen and helium onto a gas world past a specific threshold, the extra gravity squeezes the existing material into a tighter space much faster than the incoming matter can add new volume. Because of this, coal gas giants face a hard structural ceiling on their physical width, topping out right around 1 to 1.2 Jupiter radii. Hot Jupiters, on the other hand, show us a completely different path on this layout. They completely break away from this standard line, climbing up into areas of the chart that should be totally empty according to standard structural logic. They sit far above the typical path, showing off physical widths that look completely impossible for the small amount of mass they carry. When you see where this specific world sits on that layout, it looks completely isolated. It resides right on the furthest edge of the data, occupying a space where no other world can manage to last. It serves as a stark reminder that our old ways of sorting worlds simply cannot handle the extreme environments the universe creates. This planet is not just an odd data point on a chart. it represents a major challenge to our understanding of how gas worlds behave. It shows that when you push a world to its absolute limit, the old rules that govern size and weight completely fall apart. To see why this environment is so incredibly punishing, we have to look closely at the physical forces at play. The planet is pulled so strongly by its star's gravity that it has a massive structural bulge. It does not look like a smooth, round ball. Instead, it is stretched out into an oval shape, pulled toward its star by intense tidal forces. This stretching creates massive friction deep inside the world, pumping extra heat into the core and causing the gas to expand even more. The planet is caught in a destructive cycle where the star's heat swells the atmosphere, and the star's gravity pulls at that expanded gas, stretching the world out of shape. This extreme stretching also has a massive impact on how the atmosphere moves. The planet is likely tidally locked, meaning one side faces the star in permanent daylight, while the other side is trapped in endless night. This creates a massive temperature split between the two halves of the world. On the day side, temperatures climb to thousands of degrees, while the night side is significantly cooler. Massive jet streams circle the planet, trying to carry that heat around to the dark side, but the temperature gap remains huge. This constant temperature clash drives violent winds that tear through the atmosphere at thousands of miles per hour, creating a chaotic and unstable environment. The planet's low mass makes this instability even worse. Because it has less than half the gravitational pull of Jupiter, it struggles to hold onto its expanded gas. The outer layers of the atmosphere are held so loosely that they can easily be altered by outside forces. The stellar wind, a constant stream of charged particles flowing from the star, slams into the planet's atmosphere, stripping gas away and pushing it out into space. The planet has no strong magnetic shield to protect itself, leaving its outer layers completely exposed to the star's fury. This constant stripping of gas means the planet is actively shrinking over time, even as the heat tries to keep it puffed up. It is caught in a desperate tug of war between the internal heat expanding the gas and the star's forces tearing it away. This process is not slow or subtle. It is a violent and rapid destruction that is completely reshaping the world. The planet we see today is just a temporary phase in a long history of loss. When you consider the sheer scale of this loss, it becomes clear that this world cannot last. Every single second, millions of tons of gas are pulled away from the planet and lost to space forever. This gas forms a massive tail that trails behind the planet as it orbits, creating a ghostly structure that stretches across millions of kilometers. This tail is made mostly of helium, which escapes more easily than heavier elements, leaving the planet's remaining atmosphere chemically altered. This altered chemistry creates even more problems for the world's structure. As the lighter gases escape, the atmosphere becomes dominated by heavier elements, which change how heat moves through the gas layers. This can cause the planet to cool down and shrink, or it can trap even more heat, driving further expansion. The planet's internal balance is completely broken, and it is constantly shifting as it loses material. It is a world in terminal decline, running out of time as its atmosphere bleeds away. The star itself plays a massive role in this destruction. It is not a stable, quiet star like our Sun. It is a highly active subgiant that emits intense blasts of ultraviolet and X-ray radiation. These high-energy rays slam into the planet's upper atmosphere, heating the gas to extreme temperatures and giving it enough energy to break free from the planet's gravity. The star is actively cooking the planet, using its intense light to dissolve the world from the outside in. This intense radiation also causes the atmosphere to puff up even more, making it an even easier target for the star's gravity. The more the planet swells, the closer its outer layers get to the point of no return, where the star's gravity becomes stronger than the planet's own pull. Once gas crosses this line, it is pulled away instantly, creating a continuous flow of material from the planet to the star. The world is literally feeding its own parent star with its own substance. This process of mass transfer is one of the most violent events that can happen to a planet. It completely changes the orbital dynamic, causing the planet to slowly spiral closer to the star over time. As the planet gets closer, the heating becomes even more intense, the gravity pulls even harder, and the mass loss accelerates. The planet is locked into a downward spiral that can only end in complete destruction. It is moving toward a final collision that will erase it from the universe entirely. When astronomers look at this world, they are seeing a snapshot of this final phase. It is a rare opportunity to study a planet at the exact moment of its undoing. The data gathered from this world helps scientists understand how other hot Jupiters might end their lives, providing crucial insights into the ultimate fate of these extreme worlds. It shows us that the universe is not a static place, but a dynamic and often violent arena where even the largest objects can be torn apart. This realization shifts how we think about size in the cosmos. We often equate size with power and permanence, assuming that large things are built to last. This inflated world proves the exact opposite. Its massive size is a direct symptom of its weakness, a sign that it is losing control of its own structure. It is a giant made of mist, a fragile bubble waiting to burst under the glare of its host star. The story of this planet is a powerful reminder of the limits of planetary physics. It shows that there is a line that cannot be crossed, a point where a planet becomes too big and too thin to survive. This world has crossed that line, and it is paying the ultimate price. It stands as a lonely monument to cosmic destruction, a giant world that is slowly disappearing into the dark. As we continue to scan the stars for more exoplanets, we will likely find other worlds that challenge our definitions. Each discovery adds a new piece to the puzzle, forcing us to rewrite our textbooks and expand our imagination. But even in a universe full of wonders, this swollen, bleeding giant will always remain one of the most extreme and terrifying examples of what can happen when a world gets too close to its star. The final fate of this world is already written in the laws of physics. It will continue to lose mass. Its orbit will continue to shrink, and eventually it will be completely consumed. The material that once made up this massive planet will be scattered across the solar system, becoming part of the star or drifting out into the interstellar void. Nothing will remain of this giant world except the light that carries its story across the universe to us. Now look closely at how this gas is distributed across space. Because the physical structure is so incredibly expanded, the total volume it takes up means that the relationship between mass and radius for gas giants is not a simple upward curve. It is a curve that rises, peaks, and then turns over completely. The largest radii belong not to the most massive planets, but to the most inflated ones. These are planets with moderate masses subjected to extreme heating. This planet represents the absolute extreme end of this phenomenon. It is a world with less than half of Jupiter's mass, inflated by intense stellar irradiation to more than twice Jupiter's radius. The ratio of its radius to what models predict for a cold planet of the same mass is staggering. A cold, isolated planet of 0.45 Jupiter masses should have a radius of roughly 1 Jupiter radius, or perhaps slightly less. This world is more than double that. Something has more than doubled the volume this planet should occupy, filling it with the same amount of gas spread out over a vastly larger region. This massive volume has directly caused another physical property to shift, which is the planet's atmospheric scale height. The The scale height is a standard astronomical calculation that tells you how far you have to climb vertically in an atmosphere for the pressure to drop by a specific factor. For a heavy, cold world with strong gravity, the gas is pulled down tightly, so the scale height is very small. For Earth, the atmospheric scale height is about 8.5 kilometres. This world's atmospheric scale height is roughly 100 times larger than Earth's in absolute terms, and about 4 times larger even when measured as a fraction of the planet's own radius. This enormous scale height is precisely what makes the planet such an extraordinary target for atmospheric characterization. In transmission spectroscopy, the strength of atmospheric absorption features depends on the ratio of the atmosphere's annular cross-section to the stellar disk. A puffier atmosphere with a larger scale height produces deeper, more easily detectable absorption signatures. This is why multiple research teams have been able to detect a wealth of atmospheric species and escape signatures from this planet. Despite its host star's distance of 1200 light years, the planet's atmosphere is so extended that it stamps a conspicuous fingerprint on every beam of starlight that passes through it. But the same puffiness that makes the planet scientifically accessible also makes it structurally vulnerable. And this is where the story shifts from inflation to destruction. A planet's Roche lobe is the region of space within which material is gravitationally bound to the planet. Outside this boundary, material falls under the gravitational influence of the host star and escapes. The size of the Roche lobe depends on the ratio of the planet's mass to the star's mass and on the orbital separation. For this world, the combination of its low mass, its massive host star, and its tiny orbital distance produces a Roche lobe that is remarkably small relative to the planet's inflated radius. The planet fills and in fact overfills its Roche lobe. Its distended atmosphere extends beyond the gravitational boundary where material can remain bound to the planet. The gas that crosses this boundary does not hover uncertainly at the edge. It streams outward, falling toward the star along ballistic trajectories shaped by the combined gravitational fields of the planet and the star plus the Coriolis forces arising from the orbital motion. To visualize this, imagine a water balloon being squeezed through a narrow opening. The Roche lobe defines the shape of that opening. It is a teardrop-shaped gravitational boundary with its narrowest point, called the first Lagrange point, aimed directly at the host star. Gas at the top of the planet's atmosphere, heated and expanded beyond this point, spills through the narrow neck of the gravitational funnel. But unlike water pouring from a balloon in a straight line, this gas is moving as part of an orbiting system, which introduces a heavy spiral pattern to the flow. As the planet travels along its path, the escaping gas gets stretched ahead of it and trails behind it, creating a giant ring of material that circles the star. This stream acts like an open artery, letting the planet's lifeblood pour out into the void. It is a constant leakage that is completely irreversible under the current radiation conditions. This process creates a highly unusual layout for the planet's gas trail. The gas moving toward the star gathers energy and moves faster, while the gas left behind forms a vast tail. Because the planet is moving so quickly in its orbit, this tail is whipped around into a massive arc. The physical stream becomes a giant structure that can be seen using specialized telescopes on Earth. When astronomers tune their instruments to the specific wavelength of light absorbed by helium, they can see this giant tail absorbing starlight far away from the main body of the planet. This brings us to a major realization about the scale of this system. When we look at this world, we are not looking at a stable planet with a normal atmosphere. We are looking at a cosmic transition state. The material is caught in the middle of a massive rearrangement. moving from a planetary core out into a stellar disk. The planet is merely a temporary concentration of gas inside this massive flow. It is a local thickening of a stream that is being fed by the destruction of the world itself. This reality completely changes how we calculate the planet's lifespan. Old models that assumed a slow, steady loss of gas simply do not work here. The mass loss is driven by a runaway process where the more the atmosphere inflates, the more gas spills over the Roche lobe, and the easier it is for the star to pull even more material away. It is an accelerating cycle of destruction that cannot be stopped. The planet is actively burning through its reserves, and the end is approaching much faster than early theories suggested. This has led to intense debates within the scientific community about how this planet could have survived to the present day. If the mass loss is so high, why hasn't the atmosphere completely disappeared already? The answer lies in the specific history of the host star. As the star has evolved from a normal main sequence star into a subgiant, its total energy output has shifted, drastically increasing the amount of high-energy radiation hitting the planet. This means the intense mass loss we see today is a relatively recent development. The planet spent the first billion years of its life in a much calmer environment, puffed up but stable. It has only recently entered this final destructive phase. This means we are incredibly lucky to be observing this system right now. We are catching the planet during a brief cosmic moment that represents a tiny fraction of its total lifetime. It is like catching a shooting star or a collapsing building at the exact moment of its fall. The data we collect today provides a rare look at the mechanisms of planetary death, offering a wealth of information that will help astronomers refine their models of planet evolution across the galaxy. As we look closer at the details of this mass transfer, we can see that it is not a smooth process. The flow of gas is chaotic and turbulent, affected by the star's magnetic fields and variations in the stellar wind. This creates massive clumps and waves inside the escaping stream, causing the absorption signals seen by astronomers to flicker and change over time. The system is alive with activity, a violent and ever-changing environment that challenges our ability to model it accurately. The planet's core is also caught up in this chaos. As the outer gas layers are stripped away, the pressure on the deep interior drops, causing the core material to expand and change its state. This can trigger internal shifts that release even more heat, driving further inflation and accelerating the mass loss even more. The planet is literally tearing itself apart from the inside out, driven by the intense forces of its host star. This environment is far more hostile than anything found in our own solar system. Even the most extreme storms on Jupiter or the intense heat on Mercury look calm compared to the total disruption happening on this world. It is a reminder that the universe contains environments that are fundamentally different from our local neighbourhood, places where the very definition of a planet is pushed to its absolute limit. Now look closely at the deeper structural physics that this planetary layout reveals. The sheer volume occupied by this highly stretched material means that the overall balance between gravitational compression and outward thermal pressure is entirely lopsided. For a normal world, these two forces fight to a standstill, leaving the planet at a stable, compact width for billions of years. For this world, the intense heating has pushed the outward pressure to a massive victory, keeping the gas layers floating at an extreme distance from the planetary centre. This specific layout is exactly what makes the world an absolute treasure trove for astrophysical study, as it provides a naturally magnified view of gas planet physics that we can read from over 1,000 light years away. But this brings us to the final, most haunting realization about the true nature of this cosmic object. When we use the term planet, our minds naturally think of something solid, durable, and lasting. We think of a permanent celestial body that will endure through countless epochs of cosmic time. This highly inflated giant proves that our familiar definitions are far too narrow. It shows that under the right conditions of extreme heat and close stellar proximity, a planet can transform into an incredibly fragile temporary pocket of mist that is actively fading away into the dark void. It is not an enduring monument of rock or compressed gas, but rather a fleeting cosmic event, a brief moment of transition frozen in time as it bleeds its own substance into the surrounding space. This constant loss of matter means that the entire future of the system is already completely locked into a downward spiral. The planet is running out of material, and its parent star is running out of patience. As the subgiant star continues to age and expand, its outer layers will slowly creep outward, engulfing the tight orbit of the planet entirely. The world will not simply dissolve into space. It will be thoroughly swallowed up by the very star that gave it its bizarre, swollen shape. This is the ultimate fate that awaits many of the most extreme hot Jupiters discovered throughout our galaxy. They are beautiful, strange, and tragic worlds, built by the universe to burn brightly for a short moment before being completely wiped from existence. When you look back across the entire story of this unique giant, the data points leave you with a profound sense of wonder. We set out to find the single largest planet in the universe, expecting to discover an absolute gravitational powerhouse, a dense and crushing colossus that would multiply all the fiercest traits of Jupiter. Instead, the laws of physics led us to a world that is less than half as heavy as Jupiter, with an overall density lighter than a common marshmallow, and an atmosphere actively leaking into space at an incredible rate. It stands as a powerful testament to the fact that size and strength are completely different things in the cosmos, and that the grandest things the universe builds can sometimes be the most delicate and fleeting objects of all.